The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com. Hello and welcome back to the Ben Heck Show.
So what are we going to do today, Ben?
Well, in today's episode, we're going to continue working on the Hackmanji project that we started a few weeks ago. In part one of that project, we made the center of the board that the pieces moved around on magically. In today's episode, we're going to make the actual logic puzzle portion.
And that's going to use logic gates, right?
Yes, so when you roll a die, 1 to 6, that's how many places you can move if you solve the puzzle. So I want to kind of make it educational. Like in Jumanji, you just had to like run away from a zebra or jump over a boulder or whatever.
It was more just like escaping and avoiding hazards, and then once they went away, you could play again. So there was an actual skill other than evasion.
Yeah, so I want to actually make this kind of educational. So here's what I have planned. So I'm thinking logic puzzle will be, one half of the lid. So if the case looks like this, yeah, we make it fold out, and then the other half will have like the screen and like compartments to hold stuff. So when you're playing the game, you kind of turn it toward whoever's turn it is. There's your pieces there, and then the puzzle goes here, and it's like, oh my gosh, I gotta play the puzzle. Oh, like this person's like freaking out. Ah.
So in the other half of the board, there will be a button where you can roll a digital die, and then a timer will start. Like a puzzle will come up and say like, you must complete this puzzle, but it's not actually gonna say that. And then a timer will start, and then you have to.
It could say that. You must complete this puzzle. So one half we can have the screen and speakers and whatnot, and then put all the wires there.
Okay.
Then you have your game here, right? And this will be the puzzle area. So I'm thinking what we do is we have a bunch of plugs. So on the left side, we give the player source bits, like 8 source bits.
Okay.
Right? And then we'll give them patch cables so they can try to make the circuit. So we'll create some cables and use some nice banana plugs. So over here, we have kind of the answer that you're striving for. So we have 8 inputs, then we have 8 basically solutions. And we make it run in cycles. Cycle 1, you see this. Cycle 2, oh, that one's lit. Cycle 3, now that one's lit. Cycle 4, now they're both lit. So it will basically pulse that here, and then it gives you certain bits to work with. And what you have to do is use the gates. So we can have AND gates, NOT gates, OR gates, NOR gates, XOR gates, all sorts of gates. And we can just actually wire physical logic chips below the game board. So there you go. That's the plan for the logic puzzle portion of Hackmanji.
That looks like it could be a bit complicated, but I think if we get it wired up well, and we, once people like figure out how the game works, it could be really fun and educational.
Yeah, there'll be a lot of wiring, and then we have to make the puzzles, but we can ask the community for help for that.
What a great idea, Ben!
Yeah, and then we could also, work on the puzzles from now until part 3 of this project. All right, let's get started.
Amazing hacks.
Where are my dragons?
Inspired designs.
Oh, look, I knocked some hot glue loose.
Regrettable acting.
I want to live in a world with Star Wars again!
Each week, Element 14's The Ben Heck Show brings you innovative projects using electronics, engineering, and more.
Hey Ben, how are we going to lay things out on this PCB here?
We first need to think about how big the lid is going to be. So if this is our main case, we have to make 2 smaller boxes that are half the size so they can fold up onto it and also open. However, they're going to have to be the same depth as well, because otherwise, if they're not the same depth, when they open up, they're going to kind of hang down, and that'll be kind of lame. So we want them to be flat like that. So we have to make a box this deep, which means when it's closed, it'll be, fairly thick, but that's okay. And then this is inset a little bit, so we have to make sure that this is also inset a little bit so the banana plugs don't intersect with anything. We should have enough room. So this is going to be right about here. What I was thinking was we could probably do this with one perf board, and we'll lay out the chips on it. So we're using actual logic chips. So when you actually play the Logic Bomb game, you are connecting logic. Although we'll connect all the power and ground ahead of time, so the user doesn't have to do that. So all the chips will be running, just which ones you plug into. So then I got this from my buddy Parker. It's the Prop Dev Stick. It's a parallax propeller little dev board, and has everything we need. It even has an SD card, which is where we'll hold the puzzles. I guess we could put music on it too if we wanted. So we could wire this into the board as well. So we put this in here, and the power can come in on the side of the power regulation, have most of the electronics on this side of the board, Then we'll have everything here. It'll wire up to the banana plug. So maybe this opens like that, and then all the wires are there. I don't think we need a header. That's just gonna double the time it takes you to wire it up.
Yeah, okay.
Yeah, so that'll open up like that. So this will go in place. We'll just have screws in the corners to put it in the one half of the box. So yeah, whenever you wire stuff, make sure you have at least this much length to everything.
Okay.
And we'll probably have the proper real one of these like tomorrow morning. But in the meantime, you just get wires attached and just make sure they're plenty long enough.
Yeah.
Just go a little longer than you think you need. So this can we'll probably put some standoffs so this can sit down here just above the surface like that, and then it'll wire up. And then we'll have to, when we actually make this part, we'll have a hole here, and we'll have a hole here, and the wire can pass through that.
Right.
So most of the electronics are in this part of the unit, so that's where we're going to put the microcontroller. So here we've got, most everything. Here we've got the stepper motors, and up here we'll have the screen. So the further we get away from this, the fewer and fewer things there are. So we put all the electronics down here. Okay, so let's get all the chips in place, and then we can have you start wiring them up, and I will design this box so we can have a place to put them.
Okay.
So here's the folded up Hackmanji. It's about halfway done. So this is gonna unfold like this to reveal the logic bomb game. And we're still waiting on the art for this. Karen is printing it this afternoon. But just to give you an idea, this will be inset in here, and there'll be lots of banana plug jacks. So when you're given a puzzle, you'll see a message over here on the screen, which we're gonna build in part 3. And then down here, there will be 8 lights, and these will be your source lights, and they will blink in a pattern. There'll be a cycle counter going 1, 2, 3, 4, or 1, 2, or 1, 2, 3, depending on the difficulty of the puzzle. So the more dice you roll, like 1 to 6 places, then the more difficult the puzzle will be. Here will be basically the answer, and your job is, in the time required, use these inputs with these gates to replicate the answer. So Felix is working on getting a circuit board wired up. That will fit in here, and it'll use real logic gates for the patch cords, but the questions and answers will be handled by a microcontroller. So we'll be talking to those over a shift register bus. So now that I've got this box figured out and the art is in progress, I can now work on the programming.
My contribution to this part of the build is to solder all the logic gates onto this proto board. So far we have the AND, OR, NOT, XOR, flip-flop, a counter, yep, that's everything. And then we have this voltage regulator here. It can supply 5 volts at 2 amps with some capacitors on all the logic gates. And at this point, I am soldering on these lengths of wire. Basically, I cut some lengths of wire, I trim them off at an angle, or I strip the wire and then tin the leads. Now all I'm doing here is soldering the wire onto the leads of these logic gates, because I need to put on some pull-down resistors on the shift register. Figure I'll do that before I get these leads in there. I'm putting 10K pull-down resistors on the inputs of this shift register. She'll be putting on the pull-down resistors when she comes. She'll be putting on the pull-down resistors when she comes. So after I finish doing this, you'll come back and you'll see it'll be all wired up.
I've been working on the art and also starting the code for Hackmanji. This is what the game portion of it's actually going to look like, the thing that you actually have to do things on. So we have run and step buttons and cycle buttons. So the puzzle might change like state, 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 and you've got to make all 3 states match. If you want to look at one state at a time, you can hit the step button, but you have to have it in run for it to actually win, because otherwise you could step through it and just manually make the things work with the patch cables. And these will be the cycle lights to tell you what cycle you're on. So if it's a 4-cycle puzzle and it goes 1, 2, 3, 4, all 4 cycles, and you match the answer each time, then you win. So let me show you some other stuff here. This is kind of how I want to format the puzzles. So we'll do this as a text file. Here's how it works. So 3 means there's 3 states. 30 is how many seconds you get to solve the puzzle. So this could be like as high as 999 seconds, which would be a lot of time. And then this is the byte that it wants. So these are each cycle state. So here's cycle 1, it gives you this, it wants this. Cycle 2, it gives you this, it wants this. Cycle 3, it gives you this, it wants this. So the solution to this puzzle would be to use an XOR, an exclusive OR. So see how it gives you a 1 or a 1 in those states, but here when you have two 1s, it gives you a 0. I mean, that's a very simple puzzle. So that could be like a difficulty 1 puzzle. So I'm going to be using this prop dev stick, which is a microcontroller board my friend made. And this is pretty handy because it's got a SD card built into it. We could also drive an LCD with this. I created an SD card image and it has a few things on it. It has a sound effects folder, which we can use for music or whatever else we want. Voices, scary Hackmanji jungle music. And inside of this is where we have our puzzle files. So there'll be different difficulties of puzzles depending on what your dice roll is, 1 to 6. So we have difficulty 1, difficulty 6. So to achieve a 6-space move, you have to solve a pretty difficult puzzle. All right, so I've been writing the code to start this up. Let me show you how that part works. Okay, when it starts up, it will boot the SD card and then it will build a folder list. And what that's going to do is it's going to find all of the sound effect folders that are inside this folder and list their directory sectors. So how files are arranged in a system is that a folder is a lot like a file. It's just a pointer to more files, basically. So we look at the directory sector and we're like, okay, find the pointer for the SFX folder. When you go inside the SFX folder, it's going to point you to something else. It's going to point you to all the entries in that folder. And then when we go in there, we can make a list of what folders there are, which are these 3 folders. Each one of those folders is going to have another sector pointer, which points to another area that contains the list of all the files in that folder. And this allows us to basically, since we know exactly where all the files are, we can basically store the sector pointers when we boot the system to make it really easy to load things in later on. So once we get the sector pointers for all the possible sound effect folders, then we go in and we get the puzzle sector folders. So see, I'm saying, give me a file sector of PZ0 plus 1 to 6. So it's going to actually give me the sector location of each one of these text files. And we're just using 8-character file names to make it a little simpler. Okay, so let's do a test. Let's write this and then take a look at what we get. Okay, so it booted up. It found 3 sound effects folders. Cool. And it also found all 6 puzzle files. Each puzzle has been padded to fit 128 bytes, just to make it a little easier to do the math. So it's 128 bytes, so these 4 puzzles takes up 1 sector. So that's why I have buffer space goes here, please. That's just enough characters to pad it out to 128 bytes per puzzle, which is good because that way we can figure out what puzzle we want by taking 128 times puzzle number, then divide it by sector, and then jump right to it. If we are not on a 512 byte boundary, it might be a little harder to parse it, but this will make it pretty easy. So every entry has to be the same. Oh, and something to think about in a text file like this, pressing return actually adds 2 bytes. It adds carries return a new line, so that's been taken into account. Okay, so I've got the microcontroller booting the SD card properly and finding all the necessary files. The next thing I'm going to do is write some code to parse this text document that I created so it can say, oh, here's a bunch of 0s and 1s. Of course, the text document, those 0s and 1s are going to be like 48s and 49s, they're ASCII characters. We're going to parse those into bytes so the system can actually figure out what the puzzles are and then start a timer and say, okay, you've got 30 seconds to make your input match my output, go. So that's what I'm going to do next is write a parser to take this text file and make it into some game logic.
I also work at a company called The Game Crafter, which is a print-on-demand company that makes board games and card games. And we use laser cutters, and so I decided to, I offered to print our fancy game board over at The Game Crafter, and then we recently, when we acquired our laser cutters, developed a system so that we can get pixel perfect accuracy. So not only was I able to print it there, but we could cut it quite perfectly on the print. And the other nice thing is that we also, over at The Game Crafter, just got UV coating, which is really nice because I can UV coat the sticker, and when we laser cut it, all of the soot and the burn marks that are normally a pain in the butt from laser cutting just rub right off, so we can get like a nice clean print. So this is a 60-point chipboard with sticker on it, and it'll work really well and make our game board look really nice and finished.
Well, now Ms. Corbeil has put a sticker on some chipboard and laser cut this face piece that has our graphics on it. It's very nice. And then we made this backing piece so that, because the chipboard is kind of flimsy, we need it to be a little more rigid. So now it is my task to put on all of our banana plugs. So we're gonna have white, all the logic is gonna be gray, and then the result is gonna be blue. So this will take some time. Okay, so I've got all the jacks in place. Nice. 100 gray ones, 8 white and 8 blue. They're all tightened down, and I put the LEDs in place. These LEDs are going to be red, these will be green, these will be blue, and these will be green. I'm just going to start soldering those up.
All right, I got the code a little further along. This is going to load every time you need a new puzzle. It will make sure that it's not randomly selecting the same puzzle twice. Then it finds it in memory and it prints it all on the serial monitor. That's kind of pointless in the game, but obviously for debugging purposes, we want to see this. So this part right here is going to parse the ASCII file here and turn it into actual binary numbers. Because like if you load this into a computer, this isn't a binary number, this is a bunch of zeros and ones in ASCII, so it's a bunch of 48s and 49s. So we're gonna actually pull this data out, number of cycles, number of seconds, and the 4 possible sources and solutions. So let's program this and then take a look at the output. Okay, so right now it's just always going to puzzle 1, which will be the easiest difficulty, and it's just randomly selecting which puzzle to look at. So we have 0 to 7 in this case, and again, it when it loads the files in the beginning, it's like, oh, this file is 2 kilobytes long, 128 bytes per puzzle. That means there's 16 puzzles. So it always just selects a random number between 0 and the number of puzzles. Yeah, it looks like it's got everything good. So we got the number of cycles, time limit, source bits, and answer bits. Yeah, so this is looking pretty good. So the next step is I'm going to start working with Felix, who's been doing the wiring. I'm going to attach some shift registers to this, both input and output, so this thing can start a puzzle and be like, okay, here's the bits you get, here's the bits I want, cycle, 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 and then see if the answer fits. So we don't have to write a bunch of puzzles, we just have to write a few just to make sure it works, and that's the main goal of today's episode. Before I get too much further with the wiring of this, I want to just make sure that the shift registers are going to work. So I have the oscilloscope set to trigger on the latch. Okay, so we see the 8 pulses and the latch at the beginning and the end of the cycle. So these wires here will be connected to your input, which are these blue banana jacks. So we can pull one of these high to figure out the bit order, do a single capture. All right, so that'll be the LSB, cool. So we'll attach this one to 0 on our board. All right, so according to the data sheet, the MSB should be blah, 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 should be Dingus Duck. This should be the MSB, let's check. What's that mean, Uncle Scrooge? You don't want to know, laddie. I'll have your Uncle Donald explain it. I didn't learn anything. Exactly. All right, well, we know the way the bits will be loaded into the computer, so I think I can continue and wire up the output shift registers. So we have 3 shift registers, 1 input and 2 outputs. The input is your answers, and the 2 output shift registers are the source bits and the solution bits that the microcontroller will give you. So yeah, it's time for much wiring. I've got the input and solution lights hooked up along with the cycle light so we can start to see what this is going to do. So when it loads a puzzle, there will be up to 4 cycles to the puzzle, like 4 sets of lights. And you'll see the cycle lights go, 1, 2, 3, 4, or if it's just 2 cycles, 1, 2, 1, 2. So the more difficult puzzles will have more cycles to them. And these are your input lights. So what I can do is I can just pull these high. So basically you'll plug your integrated circuits into this. And what you want to do is make these match. So the computer right now is just monitoring what the input is. It's not doing the full puzzle right now. I'm just making sure that everything's hooked up correctly. But when it has a matching cycle, like right now, it'll say match. So what you have to do is not just match one cycle, but have these light pairs match on every cycle of the puzzle. And if you do that, then you've solved the puzzle. One thing that I did kind of dumb is that I had Felix wire up the gates down here. What I should have done is just put them on here upside down, like dead bug them, flip them upside down and wire them up, which I may still do, so kind of feel bad. I made Felix do all that work for nothing. But the basic concept appears to be working, so you just need to do more soldering. I wired all of the chips onto the back of the board upside down. Originally we were going to put them onto this board, but I realized that's just too much wiring. This was a lot neater of a solution. So yeah, we have a logic chips here, a flip-flop here, and a Johnson counter. So the last thing I need to add to this board are the 2 buttons. I had Felix and Karen work on the design to make some backlit buttons. They're printing now, so once they're done, I can attach them along with some switches. The buttons will also be illuminated with LEDs so we can make them blink as well, so we know their status. Once we do all that, then we should be able to do some test puzzles.
On our logic puzzle, we're going to have run and step buttons. And I was assigned the task of designing the 3D buttons that are going to go in these spots. And we're going to use some clear filament so that we can illuminate the buttons. I used 123D design. And basically I made 2 circles, extruded them up and down, made it concave on the top. And then inside I hollowed it out so that we can put our big LEDs inside, like so. So then, let's see how cool this looks. Yeah, it'll light up like this. Very nice. That's pretty cool. So when I designed these, I had to take into account the thickness of the game top and then also the plywood. So next, I need to figure out how to mount this action switch inside our box here that's gonna house all of our electronics. So I gotta figure out where this needs to be inside the box. Either I or Ben are gonna figure out how to do that.
All right, Karen, so this is the logic game portion of Hackmanji,
Okay.
which could totally be its own game.
Logic bomb
Yeah.
or something.
All right, so here's what's happening. There's a logic puzzle running, and this one looks like 3 cycles, 1, 2, 3.
Okay.
And this is what it wants. See the light?
Okay.
So on cycle 1 and 2, the light is on. On cycle 3, the light is off.
Okay.
And just ignore these. These are for testing purposes.
Okay.
And these are your source bits. So what we have to do is we have to figure out what logic gate will give us that result. And if you want to, you can hit step, and you can step through it, if you want to look at it at your own pace. However, since you could cheat by using step, you can only get a win condition if you're in run condition. So it looks like, I think this is going to be an XOR, which is an exclusive OR. That's an OR gate where one bit or the other bit, but not both bits, exclusive. One or the other, but not both. A normal OR gate, you can use both bits. So let's try it out. So let's actually put the wrong answer in. Let's hook up an OR gate, which is incorrect. So those are the 2 inputs to the gate, and this is the output. Might need a slightly longer one for that. So like, oh, maybe the answer is an OR. So what happens is it has to match all 3 cycles, and it counts 1, 2, 3 matches. So if number of matches equals number of cycles, then you win. But this is the incorrect answer, so we didn't win. So the correct answer is an exclusive OR. Well, in the game itself, if you put in the correct answer, it'll move your piece and make noise. But right now, we can just see these. If these 4 lights go flash, 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 that means we got the right answer.
But we know it was wrong because over here the blue light didn't always match the
Yep.
green lights being on or off.
So this puzzle is XOR, so this should give us a win condition.
Okay, they match?
Yep, so 1,
match.
2,
They match?
3,
Woohoo!
win!
Yay!
Yay, all right.
Oh,
so
it's
now,
flashing!
Yep, now we're
Yay!
getting, now it's loading another puzzle. All right, so here's another puzzle. It has 3 cycles. Let's see, 1,
So it's 1,
1,
0, 1, and
Then
0,
both.
1. Okay, and it's none, 0.
so let's use this AND gate here.
Okay, so we go on the AND gate.
Input 1, now go into the next input, which is there. See how the lines go into the logic symbol and come out?
Right.
So that tells you what to do.
So these are going to both go into AND?
Yep.
Okay.
And then
we're gonna
this, which might reach, will be
Ouch.
your result. All right.
What happens? What's going to happen?
Oh, you got it. Yay!
Yay!
This will be a lot better when there's like music and beeps. And we should make it like, it should be like beep. It should be like beep, 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 beep. And then it starts going faster. Beep, 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 beep.
So it'd be like a really stressful metronome.
A stress-a-gnome. Not my tempo. So that's all the time we have for today. Join us in a future episode when we complete the Hackmanji game.
And if you'd like to discuss our Hackmanji game, or if you have any questions, you can find us on the Element 14 community on element14.com/TBHS.
You can also go there to read about other upcoming episodes, builds, and special events. We'll see you next time. Hackmanji. 20 years ago, we started playing a game. Are you Sarah Whittle? Hackmanji. Hackmanji. Hey, Max. Yeah. Hackmanji. Dingus, dirty dingus duck. The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com.